replenishment of solutions, then people designed new gradient generators that include 2 channels to supply the source and sink solutions through a constant flow. So then again, so if we have the flow, then how can we eliminate any flow-induced stress in the gradient forming region? Is again to add the porous materials. So basically, so here are a few examples of source and sink, a few designs with source and sink channel with constant flow supply. So we can talk about them one by one. In panel, okay, so basically we have one source channel to supply source, one type of solution, and the sink channel to supply another fluid with a different concentration. And in between is the cell culture chamber or the gradient forming region. The gradient forming region can be the microchannel itself, like panel A shows. There are several parallel microchannels in which we have the gradient, concentration gradient, or it can be a separate channel. Like in panel B, we have the cell culture chamber. We have a separate chamber. And in between the source channel and sink channel and the gradient forming region or the cell culture chamber, we have the porous material. We have the porous structure. The porous structure, as I mentioned, can be hydrogel, can be microchannels, very small microchannel. It's like multiple pores to serve as a porous structure. So like and there are basically 2 ways. So instead of using the porous structure, there's another way to eliminate flow in the cell culture chamber, which is to keep the pressure in the source channel and sink channel exactly the same. Then without any pressure difference, then there shouldn't be any flow, right? So that is the strategy of panel A, actually. The first device, the first type of device. It's a microfluidic ladder chamber, which consists of 2 pressure balanced source and sink channels, and also multiple parallel microchannels connecting the source and sink. And so because of the pressure balance, there's no flow in the microchannels in between, and the cells are cultured in the 4 channels as shown in the figure. But all the other few examples actually uses the porous structure to eliminate flow. For example, panel B is designed with a microchannel array as the barrier between the gradient forming chamber, which is a cell culture chamber, and the source and sink channel. Okay. So here, the barrier microchannels, the height of the barrier microchannels is only 4 micron. So it's much smaller than the regular microfluidic channels, because their function is to serve as a pores, to serve as a like porous structure, right? So this array of microchannels will be the porous structure. So the channel itself is very small. And in panel C, we have in panel C, again, we have the source channel and the sink channel, and in between we have the gradient, the cell culture channel, the cell culture channel. And in between the source and the source channel and source sink channel and the center, the middle cell culture channel, we have a hydrogel in between, which is agarose hydrogel. Agarose is a hydrogel derived from the seaweed. So agarose separates these channels, and also on top of the whole chamber, on top of all 3 chambers is covered with agarose as well. Okay. So because the hydrogel has the same function as a porous membrane or microchannel array, so it eliminates flow as well. And if we apply a concentration in the hydrogel above the chamber, then this chip can also actually generate a 3D concentration profile, right? But that's not the main point of this, all of these devices. So basically, in all these designs, we have everything on the same plane, and the gradient is along one direction, from the source to the sink, right? One-dimensional concentration gradient. But if we, just in case we apply another different concentration on the top hydrogel, then we can actually generate a 3D concentration profile. And panel D had a similar structure, which also has two channels at the source and sink. And in between, the zoom in image shows that there is the middle chamber, which is actually filled with collagen gel, which is another very common hydrogel used for cell culture. So the chamber itself is filled with a hydrogel, which also, well, effectively eliminates any flow in it. So basically, the biggest advantage of microfluidic gradient generator with two source and sink channels is that they can generate a steady chemical concentration gradient over a long time, and without the need of manual replenishment of new solutions. And so the previous examples are all just a one-dimensional concentration gradient, right? So if, well, we can if we use three inlets for more than two source and sink channel. For example, in panel A here shows a round chamber with one source channel on the left and two sink channel on the top right and the bottom right. Then in this case, we can actually generate a 2D gradient, 2D concentration gradient, right? 2D, we have 2D diffusion. It's not only one dimension, but 2D on the same plane. And also we can further complicate the design by implementing 3D diffusion or 3D microfluidic gradient generators. So it's like within the whole chamber volume, we can have different, how to remove, in this case, we have a hydrogel filled the whole concentration gradient chambers. And because we have the inlets and outlets, well, connect to the chamber from all different directions. So we can generate a 3D gradient concentration profile in this chamber. These are, well, I believe the mechanism here is straightforward. So we basically have source and sink, and in between we have the gradient. Okay, then in the next, we will start to discuss the microfluidic mixers. So basically, microfluidic gradient generators generate a concentration gradient to study, well, cellular behaviors, and also basically it applies to the applications that require a fast and thorough blending of multiple constituents, right? And because in most of these devices, diffusion is the single mixing mechanism, which is relatively slow, right? So if we require very fast and thorough blending, then diffusion-based mechanism is not sufficient. So then people designed some microfluidic, so-called microfluidic mixers that makes use of both diffusion and chaotic mixing. So it's not chaotic mixing is different from turbulence, because in microfluidic devices, the Reynolds number is not high enough to have turbulence. But still, if we look at the streamlines are highly chaotic and with some vortices, for example. So the streamline, if we conduct a simulation, we can still, or if we conduct PRV experiments, we can still determine the streamline precisely. So it's still within the laminar flow regime, but the streamlines are highly complex, and so we call it chaotic mixing. And by taking use of both diffusion and chaotic mixing, we can implement a relatively fast and thorough blending or mixing of multiple fluids. So in general, we classify microfluidic mixers into passive mixers and active mixers. Passive microfluidic mixers induce the chaotic mixing of fluids by disturbing the fluid streams through some unique channel structures. And they are relatively simple. I mean, the structure of the passive microfluidic mixers are relatively simple, and they have a very low energy consumption. Basically, you just need the pump to pump the fluid through. That's it. That's the only energy required. And also, they're relatively easy to operate. So they are ideal for many applications, especially ideal for integration and miniaturization. They have relatively simple structure and easy to operate. So and active microfluidic mixers that we will discuss following this actually consumes some extra energy, external energy, to induce the mixing of fluids. So we will discuss them next. Let's first look at passive microfluidic mixers. There are some typical structures as passive microfluidic mixers, as I list here on this slide. We will discuss them one by one. So they are just different structures. So in this case, panel A is the T-junction mixer, which is exactly the same as we previously discussed. So I don't think it's we need to discuss it again. So when well, the T-junction channel can be used as a mixer when the fluid velocity is high. Otherwise, it's just a diffusion based, right? When the fluid is very high, we can see that here in the cross section, the yellow cross section shown here, we have the vortices generated when the fluid velocity is high. And panel B is twisted channels. So from its name, we can see that this type of microfluidic mixers have two twisted channels with periodic junctions along the main axis. So two fluids are injected through the two inlets into the two channels, and they combine at the junction and then split and maybe reorient and then recombine in the next junction. And this combining and splitting process repeats along the twisted channel. So by using this twisted channel structure, we can induce chaotic advection, which promotes the fluid mixing. Even at very low Reynolds number, we can still have chaotic advection. So basically in this twisted channels, the input fluids have to swing across and rotate inside the channel. So this kind of swinging and rotation induces the onset of chaos and improves the mixing efficiency. Okay. So basically what is shown in panel B here is a twisted channel mixer with 2 layers of channels crossing with each other in a periodic manner. And all the serpentine channels in this design are arranged at an angle of 45 degrees to the major axis, and the 2 channels are always perpendicular to each other, right? Okay, then panel C is
Professor?
Yeah.
Question about figure B. Where do you see the points at which these channels cross? Is that where mixing takes place?
So where mixing takes place, yeah, the mixing takes place in the whole twisted channels. So at the beginning, they are separated, but in the process, as they meet at the junction, for example, here is the first junction, and then they split, they mix here, then they split. Then they may reorient and travel to the next junction and mix here, then split again. So during this repeating periodic mixing or combining and splitting, then they, at the end of this twisted channel, they will have they will be thoroughly mixed.
Okay.
Yeah. Okay. Then in panel C is straightforward. Basically, it's a serpentine channel. So serpentine channel also promotes chaotic mixing by forcing the fluids to reorient and rotate in the channel. So this panel C shows an example that composed of a series of C-shaped sections. Okay. So it has been shown that both diffusion and convection can be increased in this serpentine channel. And then panel D, people call it a zigzag channel. So in these zigzag channels, the fluids also tend to split and recombine through the channel. Instead of, well, besides of doing experiments, people have also conducted the finite element simulation and show that the mixing, when the Reynolds number is below 80, then the mixing in such channels are mainly attributed to diffusion effect. But when the Reynolds number is above this critical number 80, then so we start to have recirculation inside the channel that induces chaotic mixing. So it requires that Reynolds number must be higher than 80 in this case. So basically, if we look at this channel, they actually, I didn't show the inlet. There is it's like a Y-shaped junction at the inlet, and then they mixed as one junction. This is, let's assume it's the first junction, and then one stream, then they split into 2 streams. One stream goes straight with this channel, and the other actually will come back, have a circulation, and then recombine with the previous stream. So there is like a circulation within this channel, and then they travel to the, okay, then at this junction, this is the next junction, it splits into 2 streams again. One goes this way and the other directly go this way. So there are multiple, this process, this structure then repeats periodically. We call it a zigzag channel. Okay, so in all these 3 passive fluid mixers, which I mean twisted channel, serpentine channel, and zigzag channel. So basically the fluid mixing is enhanced through specially designed channel structure. Right, so the channel structure guides the fluids inside to reorient, to rotate, to split, to recombine. And this causes the chaotic mixing of fluids. Then another type of passive microfluidic mixer is by including some extra structures in the channel. For example, in panel E, this is an embedded, so this is a channel with some embedded barriers. So embedded barriers, which are these square-shaped pillars, they disturb the initial flow streams to enhance chaotic mixing. And in panel E, it has this diamond-shaped obstacles. And in the same paper, the authors also actually simulate 4 types of obstacle shapes, including diamond and also circular, triangle shaped, and another shape called stepped diamond. And it was found that okay, so this is the stepped diamond shape. Stepped diamond shape. The other case is like regular, like a different pattern, also diamond shaped. And it was found that this stepped diamond shape created the best mixing effect. Okay, then in the next picture, panel F, we call it intersecting channels. Basically, this channel, in the channel, we have a series of microchannels intersecting with each other. And the fluids are divided into several substreams and then recombined by the intersecting channels. Then how to achieve these sub-channels? Basically, there are some stationary rigid elements that form the intersecting channels, which are shown in the picture. Okay. These rigid elements guide the fluid to split and recombine. And in the next panel, next picture, this is a slanted well channel. So we have this mixer in which slanted wells or slanted grooves are placed in the bottom surface of the microchannel to promote mass motion, mass transport of fluid. So it's shown that the slanted well on the floor of the T-shaped channel can effectively generate off-axis transport of flow. So basically, not only along the channel axis, but also in the transverse directions. Okay. So in this picture, basically the pattern is like some staggered herringbone pattern. Then it generates a helical flow inside the channel. So yeah, I believe the principle of passive microfluidic mixers is also straightforward. Basically, use some complex channel structure or adding some obstacle within the channel to disturb the flow stream to induce the chaotic mixing. So this is passive microfluidic mixers. Next, we're gonna discuss active microfluidic mixers. Are there any questions about the previous slide? Okay, so basically, active microfluidic mixers use actuation from external energy. So if we compare with the passive microfluidic mixers, the active mixers have even more complex structures that are usually difficult to manufacture. But because it takes use of external energy, so there's a higher possibility for active mixer to obtain a satisfying mixing effect. So it's more effective, but it consumes more energy, and also manufacturing cost is higher. So here we will introduce 6 major forms of active mixers, including acoustic actuation, electrowetting actuation, electrokinetic actuation, pressure perturbation, and thermal actuation, and magnetic actuation. So basically the last 4 types, electrokinetic, pressure, thermal, and magnetic, are relatively easy to understand. Well, acoustic and electrowetting are actually also not difficult. However, there are some interesting features in them. So I will upload 2 papers on acoustic actuation based active microfluidic mixers and the electrowetting actuation active microfluidic mixers. 2 papers on these 2 topics. And then the next Monday, the 2 presentations will be based on these 2 topics. So I will just very briefly talk about its mechanism of these 2, but we will pay more attention to the other 4 types on this lecture. So acoustic actuation is basically have 1 or more sensors which can introduce sound waves into the channels. And these sound waves move perpendicular to the flow, inducing the disturbance to the fluids and contributing to the mixing. So I didn't include any images here, which will be in the paper that I uploaded. So you will see some ultrasonic transducers are deposited on the surface of on the bottom of the channel. Sometimes on top, sometimes on the bottom, and the lateral flow of the ultrasonic waves can cause the stirring of the fluid. So this will be the first paper, acoustic actuation. And the second one, electrowetting actuation. So basically the mechanism here is that when we want to mix 2 streams of fluids, it's under the laminar conditions, it's relatively difficult. Right? However, if we just mix 2 small droplets, because of the small dimensions of the droplets, you can imagine we have 2 separate droplets. If they merge together, and then actually the mixing of these 2 of the fluids from these 2 droplets, after they merge into larger droplets, this mixing can be very fast because of the small dimension, the small size of the drops. So this electrowetting actuation actually just provides a solution for the droplet mixing. So there will be some also electrodes integrated into the microfluidic channel, which by applying an external electric field, you can manipulate the movement of the droplets in the channel to merge them, or even to separate them. Is to induce the mixing between different droplets. Then the next one is electrokinetic actuation, which actually has as shown on the top image here. So basically, when a solid surface contacts a fluid with charged particles inside, we learned before that we will have an electrical double layer appeared right next to the solid surface, right? And then if we apply an external electric potential, the fluid, well, if this electric potential or electric field can drag the charged particles to move, then the fluid will flow along with the charged particles. right? So the fluid basically tends to undergo a tangential motion with respect to with respect to the charged surface. So this phenomenon is called electrokinetic phenomenon. So basically here, also we integrate some electrodes into the channel wall in a heterogeneous manner. So it's not like, so it's like they have different positions. On bottom, we have the electrodes here, here, and here. And on the bottom, on the top, it's exactly on the opposite position. So by designing this electrode pattern, and also when we have two streams of fluids flow into this main channel, it can generate this kind of circulation next to each electrode. So this type of circulation can effectively induce the mixing of two fluid streams. This is the electrokinetic actuation. The next one is the pressure perturbation. Pressure perturbation. So we know that to run any microfluidic experiment, we need a pump to pump the fluid through the channel, right? We use syringe pumps for small volume flow rate. Thank you. Yeah. So we can imagine that if usually when we run the experiment, we have the pump running very smoothly, so running at the constant flow rate. So then the fluid is flowing also very smoothly. But we can imagine if we have a pump that operates oscillately, so meaning it maybe works for, let's say, 10 milliseconds, then stop for 10 milliseconds, and then another 10 milliseconds with the pumping, then stop for another 10 milliseconds. It doesn't have to be 10 milliseconds. It may be half second or 1 second, etc. But if the pump is running at the oscillating manner, then the fluid flow in the channel is also not smooth. It will be the fluids like activated then stop, activated and stop. So this type of oscillating pumping can apply an unsteady pressure perturbation for enhanced mixing. So when the pressure in the channel is perturbed and changed constantly, we can have a complex flow occurs in the channel to form chaotic mixing of fluids. So this is the so-called pressure perturbation actuation mechanism. The next one is thermal actuation. This is also a very interesting one. Thermal actuation, which is basically a method of applying external heating and cooling sources to form complex chaotic flow. So can you guess like why when we apply an a heating and cooling periods to the channel, we can have enhanced mixing? Can you guess what's the mechanism here? Why the alternating heating and cooling process can induce mass motion or chaotic mixing of fluids?
Molecules are moving around at different rates.
Move around in different ways. So all we apply just the heating and cooling, alternating heating and cooling.
Maybe the flow becomes turbulent.
Yeah, but why?
Concentration.
Yeah, why? Not turbulent, but chaotic. But why?
We have like a concentration flow from.
Concentration flow. Yeah, we have two fluids with different concentrations of some solutes. So why?
Viscosity. Does viscosity play a factor in that?
Viscosity, yeah, any fluids has viscosity, yeah. That's a good point, actually. So basically,
Yeah, but like the
viscosity.
mix. Oh, sorry. Go ahead. So,
You go ahead, please.
so like if it mixes with the concentration of, it changes the viscosity of the fluid. So wouldn't that play a factor in?
Yeah, this is a very good point. So basically, the fluid property varies with temperature, right? For example, viscosity. When you have heating or cooling in the channel, in different locations, the fluid has different viscosity, have different properties. So that could influence the flow behavior. That's a good point.
I
And
see.
anything else? What else that the temperature change can?
Density?
Density, exactly. Yeah. So it's very similar to the natural convection phenomenon that we discussed in fluid mechanics, right? Because the fluid density varies with temperature. So then when you change the temperature within this channel, the natural convection or density change naturally generates the mass motion of fluid, which contribute to a more efficient mixing. This is one very important mechanism. And another, besides of taking use of natural convection, another mechanism that use thermal actuation is that although we know that the fluid density also change with temperature, but still the amount is small, right? The volume change of the liquid, the volume change of liquid in response to temperature change is small, but gas is different. So when we have a gas or a bubble, when you change the temperature, when you heat it up, the volume of the bubble can swell significantly. Right. So then in some like thermal actuated microfluidic mixers, they have many gas bubbles, air bubbles, for example, in the channel. And when you heat up, those bubbles can swell, and when you cool it down, they shrink. And this kind of swelling and shrinkage of bubbles in the channel can also help induce the mixing or mass motion of liquids surrounding the bubbles. So there are two different types of mechanism for using thermal actuation, by taking use of the density change of liquids or the expansion and shrinkage of bubbles in response to temperature change. Okay, then the last one is magnetic actuation. This is also easy to understand. So for example, here in this picture showed here, the white part in the center of this circular junction here is like a rotor, which means that it can rotate in the presence of an external magnetic field, which is easy to implement. So if you have a magnetic bars, like this is basically a magnetic bar, magnetic rotor, or even you can have some magnetic particles suspended in the fluid. Then when you apply an external magnetic field or like changing electric field, then you can induce the movement or rotation of the magnetic bars or particles. And this particle or like rotor rotation can then induce the fluid to rotate as well. And then that can enhance the mixing of fluids. Okay, so here actually there are two. Oh, okay, so in this case there's only one magnetic bars, and in some other application they have two opposite placed magnetic stirrer. at the inlets of different channels, the inlets of 2 different chambers, and they all respond to the external magnetic field. So this is the mechanism of magnetic actuation. Also, sometimes people use a combination of a magnetic field and an electric field for enhancing mixing. Yeah, so these are the 4 types of active microfluidic mixers. We mainly discussed the last 4 types, and I will upload the 2 papers on acoustic actuation and electrowetting actuation for next Monday. So anyone want to volunteer to present any of these 2 topics? Acoustic actuation and electrowetting actuation. Yeah, okay, thank you, Muhammad. Muhammad volunteered to present electrowetting actuation. Anyone for acoustic actuation? Any volunteer? If not, then we will do the like sending chat message, then we will select a number and to see who will be the speaker. Yeah, so if no volunteer for acoustic actuation, then everyone, could you please send me a private message in the chat box? Everyone has to present once, yeah, throughout the semester. Okay, so messages are coming. For those who already presented, or like Muhammad, you will present, you don't have to. Any more? 1, 2, 3, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, there should be a few more. Which number we should choose for the speaker? Like the 1st or the 10th or the 15th? Which number? Or maybe let's ask, I'll ask Muhammad, who volunteered to present the electrowetting actuation. Could you say a number? Then I will see who corresponds to that number based on the private message. Pardon?
5.
5? Okay, so I'll see who is the 5th. Derek is the 1st. Insum Kim, you already presented. Dina already presented. So you 2 don't count. Michael is the 2nd. Shan Islam is the 3rd. Brenda is the 4th. Brian Kazi, you are the 5th. And Muhammad chose number 5. So Brian, Kazi, are you there?
Yeah.
Okay, so you will present acoustic actuation, the paper on acoustic actuation. This is fun. Okay, yeah, let's do this. So I will, what number is your very end. Avinash, you are almost at the end. Okay, so then we'll have 2 presentations on Monday. Okay, so I will upload the 2 papers right now onto Blackboard. Is there any other questions about today's topic? Or if you are interested particularly in any of these examples I showed today, then let me know and I can upload the papers for that.
Professor,
Mm-hmm.
do you mind explaining a serpentine channel?
Yeah. Serpentine channel is panel C here. So it's a